Okay, so we all know about pi, right? Pi is equal to 3.14159265359 and on. Pi is very interesting. It has a lot of use in math. You can use pi to find the area of a circle, or you could use it to find the circumference of a circle. You can use it to find the surface area of like a circular cone, a right circular cone, or the volume of a right circular cone. Or you can use it to find the volume of a sphere or the surface area of a sphere. You can use it to find the volume of a right circular cylinder, the surface area of a right circular this there's a lot of usage for pi in math. But I remember learning about it in sixth grade and not really understanding like how can it just go on forever? Like what do you mean it can go on forever? Well, it's not like counting numbers. Like you can make the argument that like there's an infinite amount of numbers between 1 and 2 because there's going to be an infinite amount of decimals between 1 and 2, which is great. But it follows a pattern. Like if I can go like 0. 0.1, 0. 0.2, 0. 0.3 and so on, and I can kind of follow that trend. But with pi, it doesn't seem like there's no pattern on the numbers upon first glance. Somebody was able to calculate the numbers of pi, and when I was talking to my professor, he showed me one of the ways that people use to approximate the value of pi, and it's done so using a series. So this is the series for approximating the numbers of pi. I'm going from k to infinity, so I can start plugging in numbers. If I put a 1 in the denominator where the k is, so we'll start at 1, k equals 1, then that's just going to be 1 over 1, which is going to give us 1 for the first term in the summation. 1 plus what comes after 1 is 2, so we'll do 2 in the denominator. 2 squared is 4, and thus the next term in the summation will be 1 over 4. All right, now how do we find the next term in the summation? Well, we just did 2, so we'll do 3. So we'll plug in 3 for k. 3 squared is going to be 9, so the next term in the summation will be 1 over 9. And then, by convention, we'll follow the same trend for the numbers following 3, 4, 5, 6, 7. But for now, we'll just put an ellipses to indicate that eventually, should you do this forever, you're going to get pi squared over 6. And then this expression here could be manipulated such that you can find the digits of pi alone. Let me show you what I'm talking about. Okay, so basically if I just follow this sequence, I'm going to say that pi squared over 6 is going to equal what we have plugged in for this sequence up here. And then we have to find the common denominator. The common denominator will get 36. And what we'll get for the numerator is going to be 36 plus 9 plus 4, and then that will be our rational expression. And see, now this is going to equal um, 49 over 36. And then our argument is that the rational expression 49 over 36 is equal to pi squared over 6. So then we'll multiply both sides by 6. So I'm going to say we'll multiply pi squared times 6 to cancel out that 6 in the denominator. And we'll have pi squared 49 times 6, which is going to equal 294 over 36. Is 294 divisible by 6? So we'll have 49 over 6. So that means that pi squared equals 49 over 6. But we're not interested in pi squared, we're interested in pi. So what we'll do is we will square both sides of the equation with an index of 2. Well, that's what squaring means, but these will cancel. And we'll take the square root of 49 over the square root of 6. And then this is going to equal 7 over the square root of 6. And then we're going to leave that as the square root of a 6 because it's not going to square out into a whole number. So then that means that our claim is that pi equals 7 over the square root of 6. So if you take 7 and you divide it by the square root of 6, what you'll end up with is 2.857738033. And this is supposed to equal pi. Well, that's not true because pi is actually equal to 3.14159265359, and it continues onward. This doesn't even have a 3 in it. I mean, if you round up, it's a 3, sure, but this is not what pi is equal to. Well, now that's because we only did it for the first 3 terms, and this is an approximation. So let's do it for the first 4 terms and see how this changes. So from our previous answer, we found that we had 1 plus 1/4 plus 1/9. And then it's gonna be 1, 2, 3, and then we're gonna do 4. So we'll plug in 4 for k, which is gonna be 4 raised to the second power, which is 16, and it's gonna be 1 over 16. And this will equal 205 over 144. So then to reiterate, we're saying that pi squared over 6 equals 205 over 144. But we're not interested in what pi squared over 6 is equal to. We're interested in what pi is equal to. Thus, we'll take that 6 and we'll multiply both sides by 6. And 205 times 6 is going to be 2, 4, 6, 8, 10, 1,200 plus 30, 1,230. Pi squared equals 1,230 over 144. Then we want to take the square root of both sides, so we want to take the square root of pi squared, which is going to be pi, and then the square root of 1230. I don't think that squares into a whole number because 35 squared is 1,225. So what we'll do is we'll just say this is the square root of 1,230 and then 144 12. So then let me just run this calculation. So this actually right here, this gives us the result of 2.922612986. And then from having calculated 4 terms in the series so far, this is what we're going to say that pi is equal to. Okay, but it's the same issue. Pi, we know that pi is equal to 3.141592653. Upon calculating 2 terms in the series, we find that pi is equal to 2.857738033. And then having calculated 4 terms in the series, we found that pi is equal to 2.922612986. Let me make some room. So we'll say that this here was calculated to 3 terms in the series. And then we'll say that this here was calculated to 4 terms in the series. All right. But now the issue that we're facing is that neither one of these looks like the numerical constant pi. So we can look at how the numbers change side by side. It changes a little bit. It's actually kind of large because we went from 2.8 to 2.9. And mind you, pi goes on forever. So the fact that we can even see this and recognize this change in the first integer following the decimal, mind you, I think that's pretty cool. Like that's actually substantial, in my opinion. Now, what if we calculate the first 10 terms in the series? Pi squared over 6 for the first 10 terms. What does that look like? 1 plus 1/4 plus 1/9 plus 1 over 16. So then we'll have to do 5, so we'll plug in 5 to our function in the summation. So the next term in the summation or partial sum would be 5 times 5, 1 over 25. And then the next partial sum will be 6 times 6, so 1 over 36. Then we'll have 1 over 49. Then we'll have 1 over 64. And then we'll have 1 over 100. And then the summation for the first 10 terms in this series will be written as follows. 1,968,329 over 1,270,080. So then we'll multiply 6 to the top and then square both sides of the equation. That means within the context of 10 terms, within the scope of 10 terms, pi is equal to 3.04936. So now we're getting somewhere because we know that pi is equal to 3.14159265359, and we've just calculated pi to be 3.04936 for for the first 10 terms in the summation. Now that's actually a lot better because before we weren't even reaching 3, but now we are. So this is the first right here. 10 terms. I will do the first 50 terms. Pi squared over 6 equals the summation from uh, k equals 1 to 50. And so then what happens if you sum the first 50 partial sums in the summation is that you're going to get 3.12263. That's getting closer to 3.14159265359, but we're not quite there yet. You might say that this is a lot of partial sums. 50 is a lot, right? But in the grand scheme of things, pi goes on forever. It literally goes forever. So the fact that we can even measure this, it might seem infinitesimally small. Well, not infinitesimally, but like it might seem extremely small, but it's not because we can see the change in the numbers, which even be able to measure that, for me, it's like mind-boggling and it's exciting. So, given the fact that pi goes on forever, the fact that the first 50 terms, it's approaching the digit. I mean, it's not there yet, but it's approaching the digit. It's about, oh, we're looking at the hundredths place. We're almost at 4. We almost have 3.14. We don't have it yet, but we have 3.1. And that's a little something right there. This here is the first 50 terms. So what about for the first 100 terms? What about for the first 500 terms? What about for the first 1,000 terms? What about for the first 10,000 terms? What's going to happen? How can we continue to approximate pi to infinity? For the first 100 terms, we're going to end up with 3.13208. That's so close to 3.14. The famous 3.14. That's so close, but it's not there. So what about for the first 500 terms? For the first 500 terms of the summation, you'll end up with 3.13968. Let's take a moment to recognize the pattern here. Even upon increasing the amount of partial sums in the summation, the rate of change is starting to get smaller and smaller and smaller. So for the first 3 terms, we had 2.8, and then for the first 4 terms, we had 2.9. It went from 2.8 to 2.9. The first unit in the tens place changed. The first unit following the decimal changed. Now we went from the first 100 terms, 3.132, to the first 500 terms, 3.139. And you'll find that the only integer, the only digit that changed within the number following the decimal. So what that tells me is that the rate of change is starting to get smaller and smaller and smaller. It's thinning out, akin to prime numbers and their prevalence within the counting numbers. But that's a whole nother thing. Maybe I'm trying to draw a comparison where there is none. I don't know. I'm just sitting in my room with my cat trying to approximate pi to infinity. Anyway, I digress. So let's do the first 1,000 terms. The first 1,000 terms within the summation will give us 3.14064. How profound is that? We have a formula to literally approximate pi to infinity. That is revolutionary. Oh, wait, hold on, wait. Before I go on, so now we have the first 1,000 terms. The first 1,000 terms gives us the famous 3.14. But what about the first 10,000 terms? What happens? 3.1415. And that's starting to look a little bit like what we have up top. It's not quite there yet. Now, pi does go on forever, so the fact that we can even try to measure this, and when we can get somewhere with the first 10,000 terms, it might seem really large, but for me, it seems kind of small given the fact that pi goes on forever. But it's profound that we can quite literally calculate pi to infinity with this little formula here. This formula is humble, it's simple. It doesn't look like much, but you can literally calculate pi to infinity with it, and that is just so cool. And I'm just so excited, and I'm so happy, and I'm so grateful that my professor showed this to me. Shout out to my professor, Michael Farquhar, who showed me how to do this in the first place. This is something that really shows the power within a series. This just makes me so like, I don't have the words. It just makes me excited. It's just something really special. And I hope that this excites you guys as much as it excites me. And I hope you have a good day. Thank you so much for watching my video.